The last thing we look at when we're thinking about equilibrium reactions is what happens to them when we have a change to them, such as changing the temperature, changing some concentrations of reactants or products, changing the pressure, or adding a catalyst. When we're thinking about this, we're going to think about this concept known as Chatellier's principle. And it was, I guess, derived or written down first by Mr. or Dr. Chatelier, French chemist, and he would describe that when a chemical system that's sitting at equilibrium, that's when the forward and reverse reactions are happening at the same speed, the equilibrium will shift its position to counteract or to go against or undo any change that it experiences. So basically, an equilibrium system will try to undo what you did by doing the opposite. The only time it can't undo this and get back to the original equilibrium position, equilibrium constant, original ratio of products to reactants, is when we change temperature, and we'll get back to that later. The first factor we look at is concentration, and because Kc is a constant, it will start to say the same number except for temperature, which we'll look at later. So if we change a concentration on either side in reactants or products, then the reaction will shift to either the products or reactants to try to get back to that position where the ratio is back to the original ratio of products to reactants. So if I increase my reactants, and the number that comes out, if I put it into the equilibrium expression, let's say Q, we'll call it Q, that means that will be lower than what it should be, because I'll have more, this has gone up, so therefore the number will come down. So to get back to Kc, that means that the products will need to go up and reactants come down, and the way to do that is that the reaction proceeds to the right to undo that, so it favours the products. And likewise, if I do that again for the same sort of scenario with the products, it just is the reverse of that. We get too many products, Q is too high, products will get converted to reactants to get back to Kc. So for example, if we've got this reaction here, ethanoic acid, which can deprotonate in water, if I add more of ethanoic acid to keep Kc constant, the reaction, the numerator, so this is the top bit here, which is the products, has to get bigger if this has increased. So I've got to increase my products and decrease my reactants. So to do that, the reaction must proceed to the right towards products. In this same reaction, but another example, if we have some sodium hydroxide added to the solution, what would happen? Well, the hydroxide react with H+, so that's going to remove and decrease the concentration of H+. So that will cause Q to go down in value. To therefore adjust for that, to undo that, we need to increase products and again decrease reactants. So we're going to favour the forward reaction to make more products to get back to Kc. So here are the scenarios. If the equilibrium shifts to produce more products or more reactants to keep Kc constant. So if an increase in reactants is going to shift to minimize the increase in reactants by producing more products, favoring the forward reaction. If we decrease the reactants, the equilibrium system will move to minimize the decrease in reactant concentration by producing more reactants. This favors reverse reaction. Increase in products will favor the reverse reaction to produce more reactants, whereas a decrease in products, in the example just seen, will shift towards the product side, favoring a forward reaction. One more example on concentration. So here we have ammonia being produced from nitrogen and hydrogen. If we're going to increase the nitrogen concentration, that means that Q would be going down because the denominator of Kc would be too high. To undo that, it's going to lead to the reaction going to the right to make more products, to increase more products and decrease reactants. So concentration of NH3 in response will go up. If we increase ammonia, well, that would make Q too big. So it will have to go, reaction would have to favour going in reverse to the left so that we can decrease the products and increase the reactants. So in this case, the concentrations of nitrogen and hydrogen would both increase in value. If we decrease in the concentration increase in the concentration of nitrogen, well, that would result in Q being higher because I'm removing some of the reactants. Again, so the reaction will shift to undo that, replace the reactants by decreasing products and increasing reactants by shifting towards the left. If I now remove some ammonia, that would decrease the Q. So to undo that, would have to favour the right reaction, the forward reaction, to produce more products to replace those that have been lost and decrease the reactants. Second effect is the effect of pressure. One good thing to remember is that 1 mole of gaseous particles takes up the same volume irrespective of how big it is. So 1 mole of hydrogen is the same volume as a mole of methane or N2O4. Doesn't matter what it is. So we can just think about, in this example, just think about total number of moles of gaseous particles. And the equilibrium shifts to favour products reactants to keep Kc constant. And again, trying to undo what we do. So if we increase the pressure, which is the same as decreasing the volume, it wants to minimize the increase by decreasing the pressure. So it's going to favour the side with the least number of gaseous particles, because the more particles in there, the higher the pressure. So in reverse, if I decrease the pressure by increasing or increase the volume, you're going to try to minimize that decrease by increasing the pressure, therefore favouring the side with the greatest number of gaseous particles. So looking back to our example of ammonia, if I am increasing the pressure or decreasing the volume, I'm going to look at my equation. On this side I've got 4 moles of gas, and on this side I've got 2 moles of gas. So if I increase the pressure, I will favour moving to the right to make more products, because there on the product side there's 2 moles, whereas on the reactant side is 4 moles. If I decrease the pressure by increasing the volume, I've got the reverse of that situation. I want to increase the equilibrium system, will try to undo that and therefore make more moles, so it will go in reverse. And in doing that, it's going to increase the products, the reactants being made. So that is the effect of pressure. The final effect is the effect of temperature, and this is the only factor that changes Kc. And the reason why that is when you change the temperature, you're changing permanently the amount of energy being given to a system. And so that energy can constantly be supplied, and so that it will shift what is favoured. And we've got to cast our mind back to the thing we learned about endothermic and exothermic reactions. So if we do our little scales here, we've got this one here as being exo, and this one here is being endo. Now, if we're one of these reactions, if the if it's a reversible reaction, going this way is exo, but if I go back that way, it's endo. Likewise, if it's this way is endo, the reverse is exo. So we've got to bear that in mind, that's be helpful. Because endothermic needs that extra energy to increase that total energy in the system, increasing temperature favours the endothermic reaction. This is the key phrase. Make sure you memorize this, learn this. Increasing temperature favours the endothermic reaction. Alright? Very important to remember that. Because you're providing more energy that can be absorbed. So the opposite, therefore, is if the decreasing temperature favours the exothermic. Because it's removing the energy that's released. And if an equilibrium reaction is in an equilibrium reaction, if the forward reaction is endothermic, the reverse will be exothermic, just what I've shown up there. So, highlighting this, temperature is the only factor that changes Kc. If you get a question about the other ones, how does a change in volume or pressure or catalyst or concentration affect Kc? It does not affect it. Only temperature does. So, turning to our example here of ammonia, if we look at this delta H, we can see that it is negative, therefore it is an exothermic reaction. So that tells us this reaction is forward exo, and therefore reverse must be endo. So what are our scenarios? If we're increasing temperature, let's remember before, increasing temperature favours the endothermic reaction. Another way of thinking about that is if we include heat as either a product or reactant, in this case it's going to be a product because exothermic, releasing heat, producing heat. So we've got that, there is heat, so if you're increasing temperature you're like adding more heat. Therefore, you're going to be like adding a product, therefore it's going to try to undo that, make more reactants. So it's another way of thinking about it. Increasing temperature favours the endothermic reaction, so in this case it's going to be a reverse reaction, we'll shift to the left, therefore that's going to increase reactants and decrease products. And so if we look at Kc, that's going to have a permanent effect because the products have gone down, reactants have gone up, so Kc's value will decrease. That's a permanent decrease. Second scenario is if we decrease the temperature, and that's like removing heat. And if we're like removing a product, we're going to try to undo that and produce some more. So it's going to shift towards the right hand side to the products. So we're going to increase in products, decrease in reactants. That's going down, that's going up, so therefore Kc in this case will increase with decreasing temperature. But we can all solve this scenario if we can remember that increasing temperature favours the endothermic reaction, key phrase which we can then use to kind of work with this. Final thing to think about is the catalyst. Now the catalyst has no effect on the reaction, because basically what it does, it speeds up both the forward and the reverse reactions. So the equilibrium system or reaction gets to the equilibrium point faster, but the Kc stays the same as the uncatalyzed reaction. So it has no effect on the equilibrium, no effect on Kc. So that's the factors that affect equilibrium systems, where only temperature affects the value of Kc. All the other ones will shift to undo the effect of the change.